What problems were computers originally invented to solve?
Originally, computers were invented to solve numerical problems. Now, very few mathematicians, scientists, computer scientists, and engineers can imagine a world without computers. Advances in technology have also led to an increase in accuracy, the number of problems that can be solved, and the speed in solving those problems a far cry from the earliest computers.
What are some other types of analysis?
There are numerous other analyses in mathematics and the sciences besides vector analysis. At one time, the study of tensors was known as the absolute differential calculus. But today it is simply called tensor analysis. Tensors were originally invented as the extensions of vectors. Tensor analysis is concerned with relations or laws that remain valid, regardless of the coordinate system used to specify the quantities. Complex analysis, or complex variable analysis, is the study of complex numbers and their derivatives, mathematical manipulations, and other properties. It is mostly used to find the solution to holomorphic functions, or those that are found in a complex plane, use complex values, and are differentiable as complex functions. Complex variables deal with the calculus of functions of a complex variable, incorporating differential equations and complex numbers. For example, one such variable of the form z equals x plus e, in which x and y are real and the imaginary number I equals -1. Complex variable techniques have a great many uses in applied areas, such as electromagnetics. Functional analysis is concerned with infinite-dimensional vector spaces and the mapping between them. It is also considered the study of spaces of functions. Finally, differential geometry is really a branch of geometry, but it includes the concepts of the calculus as applied to curves, surfaces, and other geometric entities. Originally it included the use of coordinate geometry. More recently it has been applied to other areas of geometry, such as projective geometry. In particular, differential geometry uses techniques of differential calculus to determine the geometric properties of manifolds. A topological space that resembles Euclidean space, but is not.
What is topology?
In general, topology is a branch of mathematics that examines patterns of geometric figures based on position and relative position without regard to size. It has also been called rubber sheet geometry because objects examined in topology are under continuous transformation. Also called topological transformation or homeomorphism. The shapes can be stretched, bent, and twisted in various ways, as long as they are not torn or cut as they are changed. For example, A circle is considered to be topologically equivalent to an ellipse. It can be deformed by stretching, and a sphere is equivalent to an ellipsoid. This includes changing an object based on a one-to-one correspondence. For more about changing such shapes and one-to-one correspondence, see elsewhere in this chapter.
What is GIMPs?
GIMP stands for the Great Internet Mersenne Prime Search. A program started in January 1996 to discover new world record-sized Mersenne prime numbers. It harnesses the power of the Internet and thousands of small computers belonging to public and private concerns to make the necessary calculations. GIMPs uses only about 8 megabytes of memory and about 10 megabytes of disk space. Per computer, a small amount of space for such a large undertaking. A Pentium-class computer is necessary, and the computer should be on most of the time. But if you decide to join the GIMPs group, be patient. A single test can take about a month to complete. To find out more, get on your computer, log on to the Internet, and access the address http://www.mersenne.org/prime.htm.
Who was Omar Khayyam?
Omar Khayyam, 1048 to 1131. Who was actually known as Al-Khayyami, was a Persian mathematician, poet, and astronomer. He wrote the treatise on demonstration of problems of algebra, a book that contains a complete classification of cubic equations with geometric solutions, all of which are found by means of intersecting conic sections. He solved the general cubic equation hundreds of years before Niccolò Tartaglia in the 16th century. But his work only had positive roots. Because it was completely geometrical, see elsewhere in this chapter for more about Tartaglia. He also calculated the length of the year to be 365.24219858156 days, a remarkably accurate result for his time, and proved that algebra was definitely related to geometry.
How did money evolve?
Before the advent of money, exchanging goods was merely a matter of bartering. Livestock and grains often were used in ancient times as methods of barter, with one item exchanged for another. But there were definite limitations to this. For instance, if a farmer wanted to barter for a horse with wheat in the winter, he would have to know how to store the wheat in order to get the horse. Timing became essential, and sometimes meant the difference between surviving and dying. Some of the first types of money included limestone coins, ranging in size depending on their value. Tobacco, shells, whale's teeth, and even bread in medieval Iraq. The use of gold and silver coins is thought to have started around 650 BCE by the Lydians, who lived in the area between the Black and Mediterranean seas. Before that, metals were traded as money in other forms, such as nuggets, rings, and bracelets. Paper currency first appeared about 300 years ago and was usually backed by some standard materials of natural value, such as gold, that could be converted on demand. Using currency was a great improvement over the bartering system. Although bartering still has its place in many countries, especially throughout smaller communities. For example, when gold became a trade standard, it was easier for the farmer to buy the horse in the winter with gold coins than try to store enough wheat, and keep away mice, to make the trade. In the West, as more and more people participated in the gold standard, the banking industry grew, paralleling the growth of trade and industry. Today, monetary systems are deeply entrenched, with various types of currencies in a multitude of countries. Type of money keeps changing, too. For example, in 1988 the world's first durable plastic currency was introduced by Australia. Plastic bills were seen as a way to frustrate counterfeiting. In 2000 the European Economic Community introduced the euro, a monetary unit that puts much of Western Europe under a common currency. All this exchanging and changing of currency involves, of course, mathematics.
Who were the Akkadians?
The region of Mesopotamia was once the center of the Sumerian civilization, a culture that flourished before 3500 BCE. Not only did the Sumerians have a counting and writing system, but they were also a progressive culture, supporting irrigation systems, a legal system, and even a crude postal service. By about 2300 BCE, the Akkadians invaded the area, emerging as the dominant culture. As most conquerors do, they imposed their own language on the area and even used the Sumerians' cuneiform system to spread their language and traditions, although the Akkadians brought a more backward culture into the mix. They were responsible for inventing the abacus, an ancient counting tool. By 2150 BCE, the Sumerians had had enough. They revolted against the Akkadian rule, eventually taking over again. However, the Sumerians did not maintain their independence for long. By 2000 BCE their empire had collapsed, undermined by attacks from the west by Amorites and from the east by Elamites. As the Sumerians disappeared, they were replaced by the Assyro-Babylonians, who eventually established their capital at Babylon.
What does the strange symbol IFF mean in calculus?
He symbol, or word, IFF actually is shorthand for if and only if. It is not only mathematics that depends on the IFF, but also philosophy, logic, and many technical fields. It is usually italicized, in addition. The phrase P is necessary and sufficient for Q is also seen as QIFFP. The corresponding logical symbols for if and only if are, and equals. But for those who study calculus, it is an area of mathematics pioneered by Gottfried Leibniz. His idea was based purely on the concept of infinitesimals. This was in opposition to the calculus of Isaac Newton, who based his calculus on the concept of the limit. Although historically the emphasis was placed on the minute. Modern infinitesimal calculus actually has little to do with infinitely small quantities.
What is quantum mechanics?
Quantum mechanics is a branch of quantum theory that simply determines the probability of an event happening. Although the mathematical calculations to prove such things are very rigorous and complex. In fact, quantum mechanics is often called the final mathematical formulation of the quantum theory. Developed during the 1920s, it accounts for matter at the atomic level and is considered an extension of statistical mechanics, but is based on quantum theory. One important part of quantum mechanics is wave mechanics, which is an extension of quantum mechanics based on Schrödinger's equation. This idea states that atomic events can be explained as interactions between particle waves. For more on Erwin Schrödinger, see History of Mathematics.
Who was Hipparchus?
Hipparchus of Rhodes, also seen as Hipparchus of Nicaea, as he was born there, c. 190 c. 120 BCE, was one of the greatest Greek astronomers. A partial list of his discoveries includes, being the first to discover the precession of the equinoxes, compiling an extensive star catalogue, assigning magnitudes as a measure of stellar brightness, and calculating the length of the year to within 6.5 minutes of the correct value. His planetary models were mathematical, not mechanical. And although Hipparchus did not invent it, he was probably the first person to systematically use trigonometry, which was a necessity for most of his discoveries.
What is differential calculus?
Differential calculus is the part of the calculus that deals with derivatives.
What is density?
Density, usually abbreviated as D or R, is a mathematical concept used to describe the ratio between the mass of an object and its volume. The actual formula is the density times the volume is equal to an object's mass, or dxv equals m. In the standard, American, measurement system, density is measured in pounds per cubic foot. But in the sciences, the metric system is usually used and density is measured in grams per cubic centimeter, or grams per milliliter. For example, the density of water is 1 gram per cubic centimeter. Lead is 11.3 grams per cubic centimeter, and gold is 19.32 grams per cubic centimeter. Note, in the majority of cases, the higher the density, the heavier it feels to us on Earth.
What are some numbers associated with tire pressure?
Tire pressure is measured using a tire pressure gauge, with the most common measuring device being about the size of a pen. First, a bit about pressure. The atmosphere at the surface of our planet measures about 14.7 pounds. 6.67 kilograms per square inch, or a 1 inch, 2.54 centimeters, square column of air weighs 14.7 pounds. This changes depending on the altitude. For example, at an altitude of 10,000 feet, 3,048 meters, the air pressure decreases to 10.2 pounds, 4.63 kilograms, per square inch. But a car, truck, SUV, or bike tire needs more pressure in order to inflate. By increasing the number of atoms inside the tire, there are more collisions between the atoms and more pressure exerted on the sides of the tire. In other words, a pump stuffs more air into a constant volume. The confines of the tire, so the air pressure within the tire rises. A car tire's pressure is typically at about 30 pounds, 13.61 kilograms, per square inch. A bicycle tire's pressure can be around 90 pounds, 40.82 kilograms, per square inch.
What are deduction and induction and how are they used in mathematics?
Deduction in logic is when conclusions are drawn from premises and syllogisms. For more information on these terms, see above. In this instance, a deduction is a form of inference or reasoning such that the conclusion is true if the premises are true, or, based on general principles, particular facts and relationships are derived. Deductive logic also means the process of proving true statements, theorems. Within an axiomatic system, if the system is valid, all of the derived theorems are considered valid. For example, if it is known that all dogs have 4 legs and Spot is a dog, we logically deduce that Spot has 4 legs. Other examples of deductive reasoning include Aristotle's syllogisms. Induction is a term usually used in cases concerning probability, in which the conclusion can be false even when the premises are true. In contrast to deduction, the premise provides grounds for the conclusion, but it does not necessitate it. Inductive logic generates correct conclusions based on observation or data. but note that not all inductive logic leads to correct generalizations. Making the validity of many such arguments probabilistic or iffy by nature. One can see how both these processes work in the scientific world, especially in the scientific method in which general principles are inferred from certain facts. For example, by observation of events, induction, and from principles already developed. Deduction, new hypotheses are formulated. Hypotheses are then tested by applications. And as the results satisfy the conditions of the hypotheses, laws are developed by induction. Future laws are then often developed, many of them determined by deduction.
What did Isaac Newton contribute to mathematical analysis?
English mathematician and natural philosopher, otherwise called a physicist. Isaac Newton, 1642 to 1727, was one of the greatest scientists who ever lived. Overall, he contributed to physics, such as the discovery of his three famous laws of motion, fluid dynamics. Fluid motion, the union of terrestrial and celestial mechanics using the principle of gravitation thus. Explaining Kepler's laws of planetary motion, and he even explained the principle of universal gravitation. By 1665 Newton had not only begun his work on differential calculus, but he also had published one of his greatest scientific works, Philosophiae Naturalis Principia Mathematica. The mathematical principles of natural philosophy, often shortened to the Principia or just Principia. In it he presents his theories of motion, gravity, and mechanics, thus explaining the bizarre orbits of comets, tides and tidal variations, the movement of the Earth's axis, called precession, and motion of the Moon. And although he used calculus to find many of his scientific results, Newton also explained them using older geometric methods in the book. After all, calculus was very new. Perhaps he was the first scientist writer to make sure everyone understood what he was proposing.
What does carry mean in addition?
In addition, carry defines a way in which larger numbers are added. In this arithmetic operation, there is a shifting of leading digits into the next column to the left when the sum of that column exceeds a single digit. For example, carrying is evident in the following operation in the base 10 numbering system. Adding addends 234 and 168, giving the sum 402 234 plus 168 402 by adding the same columns. Starting in the right-hand column, 8 plus 4 is 12, a number larger than 9, the highest number then can exist in that spot. Carry the amount of 10 to the next column, leaving 2, add 3 plus 6 plus 1, which, when carried, represents 10 for this column, which equals 10, again a number larger than 9. Again, carry the 1 to the next column leaving 0, Adding the 2 plus 1 carried, equals 4. All total, the sum is 402.
What are some interesting facts about the Julian and Gregorian calendars?
An interesting fact about the Julian calendar is that it designates every fourth year as a leap year. A practice that was first introduced by King Ptolemy III of Egypt in 238 BCE. A quirk about the Gregorian calendar is that the longest time between two leap years is 8 years. The last time such a stretch was seen was between 1896 and 1904. It will happen again between 2096 and 2104.
What is the difference between a mini-computer and a microcomputer?
The term mini-computer is not used much today. It is considered to be the type of computer built mainly from about 1963 to 1987. And refers to the mini mainframe computers that were not large enough to be called mainframes but were large enough to take up the space of a small closet. These computers were once popular in small businesses that could not afford the money or space for a mainframe computer. They were much less powerful than a mainframe and were limited in hardware and software. And they were built using what was called low integration logic integrated circuits. Eventually, they were overtaken by microcomputers built around the microprocessor. The microcomputer was a later development in computing. It was developed as a general-purpose computer designed to be operated by one person at a time. The single-chip microcomputer, complete with microprocessor, was, in many respects, a landmark development in computer technology, resulting in the commercialization of the personal computer. This is because computers became smaller and less expensive, and the design made parts easier to replace.
What is Euclidean geometry?
Euclidean geometry is named after Euclid, the famous Greek mathematician. It is geometry mostly based on Euclid's fifth postulate, the parallel postulate, and is sometimes called parabolic geometry. Plane geometry is described as two-dimensional Euclidean geometry, while three-dimensional Euclidean geometry is known as solid geometry.
Why is there no Nobel Prize for mathematics?
The Nobel Prizes were established at the bequest of Swedish chemical engineer Alfred Bernhard Nobel. 1833 to 1896, the discoverer of dynamite. First awarded in 1901, the Nobel Prizes honor innovators in the fields of chemistry, physics, physiology or medicine, literature, and peace. A prize in economics was added in 1969, but there is no award for mathematics. The lack of a mathematics prize has many stories attached, including one that states that Nobel's wife jilted him for Norwegian mathematician Magnus Goestemiddag-Leffler. A notion made less plausible by the fact that Nobel never married. Most historians agree, however, that the reason has to do with Nobel's attitude toward mathematics. He simply did not consider mathematics sufficiently practical. To fill the gap, the Fields Medal of the International Mathematical Congress was established in 1932. It has the equivalent prestige of the Nobel, with the limitation that it is only awarded for work done by mathematicians younger than 40 years old, and the monetary value is a mere $15,000 in Canadian dollars, or about $12,000 in US dollars at press time. But mathematics has not been left out of award-winning ceremonies. In 2003, Norway created the Abel Prize for Mathematic Achievement, named after Norwegian mathematician Niels Henrik Abel, 1802–1829, who proved that solving fifth-degree algebraic equations, quintics, is impossible. The award gives the winner a prize of 6 million Norwegian kroners, about $935,000 in American currency.
How is math used in statistical process control?
Statistical process control, SPC, involves using statistical techniques to measure and analyze the variations within a process. With SPC, industrial engineers monitor, control, and ideally, improve a process through statistical analysis. The 4 basic steps include measuring the process, eliminating variables within the process to make it consistent, monitoring the process, and finally, improving the process to make the, usually better, intended product. But it is not the answer to everything. All the SPC does is ensure that the product is being manufactured and designed as intended. Thus, SPC does not tell whether the design is good or bad, just if it's made according to plan.
How do I make change?
Making change is an important monetary endeavor no matter where a person travels or lives. It is defined as the change, in coins and/or bills, a customer receives after making a purchase. Especially when the customer gives the merchant more money than the amount due. For example, say a person visiting a farmer's market in the United States buys a half pound of garlic for $2.60 and gives the merchant a $20 bill. To make change, the merchant would first subtract $20. $2.60 equals $17.40. Or the customer is to receive $17.40 in change. The resulting change would start with the highest denomination and work down, a $10 bill. A $5 bill, 2 $1 bills, a quarter, 25 cents, a dime, 10 cents, and a nickel, 5 cents. The merchant would then count the change out to the customer, stating each amount in the opposite fashion. That's a total of $2.60 out of $20, your change is $2.65, $2.65 as the nickel is given. $2.75, $2.75 as the dime is given, $3 as the quarter is given. $4 as the first dollar bill is given, $5 as the second dollar bill is given. $10 as the $5 bill is given, and 20 as the $10 bill is given.
Who developed analytic geometry?
Analytic geometry began when French philosopher, mathematician, and scientist René Descartes, 1596–1650, in Latin. René Descartes published a work explaining how to use coordinates for finding points in space. He was the first to make a graph and presented a geometric interpretation of a mathematical function. This marked a step toward what is now known as Cartesian coordinates, a term derived from Descartes' Latin name. Around the same time, an independently French mathematician Pierre de Fermat, 1601–1665, also did much to establish the ideas of coordinate geometry. But, unlike Descartes, Fermat did not publish his work. Both Descartes' and Fermat's ideas would lead to modern Cartesian coordinates. For more about Descartes and Fermat, see History of Mathematics.
What are some examples of logarithm use?
Logarithms are used in many areas of science and engineering, especially in those areas in which quantities vary over a large range. For example, the decibel scale for the loudness of sound and the astronomical scale of stellar brightness are both logarithmic scales. Log A equals 1, because A equals A. For example, in the equation 31 equals 3, the base is 3 and the exponent is 1, the result is 3, with the corresponding logarithmic equation being log 3 equals 1. X 4 log A equals X, because A equals A. For example, 4 equals 3, with the base as 3. The logarithmic equation becomes log 3 equals 4.
Why can't you divide by 0?
Dividing by 0 is like the old saying, you can't get something from nothing. Mathematically speaking, it's the same way, you can't divide by nothing. In fact, when something is divided by 0, the answer is always undefined. Here are a few ways of looking at this. There is a rule in arithmetic that a, b/a, equals b. So if we say that 1/0 equals 5, then 0, 1/0, equals 0 x 5 equals 0. In other words, If you could divide by 0, this rule would not work. Another way to look at the no to 0 as a divisor problem is through multiplication. If 10 halves equals 5, we know that 5x2 equals 10, the same for 5/1 equals 5, thus we know that 5x1 equals 5. But if you take 5/0, that would mean that the answer times 0 would equal 5, but anything times 0 is equal to 0. Because there is no answer to this dilemma, mathematicians say you can't divide by 0.
Who was Charles Babbage?
English inventor and mathematician Charles Babbage, 1792 to 1871. Is considered by some historians to be the father of computing. The main reason was his analytical engine, which is thought to be the true precursor of the modern computer.
What types of analyses interest engineers?
There are several types of analyses that interest engineers, all of which involve mathematical modeling. Structural analysis deals with linear and nonlinear models and stresses on a material. The linear models assume the material does not plastically deform, the remaining deformation after the load causing it is removed. Nonlinear models stress the material past its elastic capabilities. The stresses in the material then vary with the amount of deformation. Vibrational analysis deals with possible resonance and subsequent failure. It is used to test a material that may experience random vibrations, impacts, or shocks. Fatigue analysis is used to determine the life of a material or structure. It shows the effects of occasional, periodic, or cyclic loading on a structure or object, pointing out where cracks or fractures are most likely to occur. Engineers measure heat transfer to determine a material or structure's conductivity or thermal fluid dynamics. In this way, researchers understand how a material will respond to various hot and cold conditions, or even how it diffuses heat and cold over time.
How was, and is, 1 second defined?
A second was once defined as 1/86,400 of a mean solar day. By 1956 this definition was changed by the International Bureau of Weights and Measures to 1/31,556,925.9747 of the length of the tropical year 1900. But like most measurements, the second definition changed again in 1964, when it was assigned to be the equivalent of 9,192,631. 770 cycles of radiation associated with a particular change in state of a cesium-133 atom. Interestingly enough, by 1983 the second became the definer of the meter. Scientists defined a meter as 1/299,792,458, the distance light travels in 1 second. This was done because the distance light travels in 1 second was more accurate than the former definition of the standard meter.
Who developed the idea of a foot in measurement?
Here is quite a mystery about who first developed the foot as a measurement unit. One story, which most scholars believe is a legend, is that a foot was the length of Charlemagne's 742 to 814 foot. Charlemagne, also known as Charles the Great, was king of the Franks and emperor of the Holy Roman Empire. Standing at 6 feet 4 inches tall, he probably had a really big foot. Still another story involves England's King Henry I. 1068 to 1135, in which the length of an arm became important. Henry I ruled that the standard foot would be 1/3 of his 36-inch long arm. This thus became the origin of our standardized unit of 12 inches to a foot. The inch being 1/36 of a yard, according to the Oxford English Dictionary. The first confirmed usage of the word foot as a unit of measurement also occurred during the reign of Henry I. In honor of his arm, he ordered that an iron ulna, the ulna being the longer, inner bone in the forearm, be made. This iron stick represented the master's standard yard for the entire kingdom. But around 1324, in response to his subjects' cries for an even more standard measurement, England's King Edward II, 1284 to 1327, changed things again. Recognizing the iron ulna was not universally available, he declared that 3 barley corns, round and dry, make an inch, and that 12 inches, or 36 barley corns, would equal 1 foot. It's interesting to note that even shoe sizes were tied to King Edward II and barley corns. He declared that the difference between one shoe size to the next was the length of 1 barley corn.
What was the golden age of logic?
Ert Gödel's work led to what is often described as the golden age of logic. Spanning the years from about 1930 to the late 1970s. It was a time when there was a great deal of work done in mathematical logic. From the beginning, mathematicians broke into many camps that worked on various phases of logic. For more information about logic, see Foundations of Mathematics, including proof theory, in which the mathematical proofs started by Aristotle and continued by Boole, CP 30, were extensively studied, resulting in branches of this mathematics being applied to computing, including artificial intelligence. Model theory, in which mathematicians investigated the connection between the truth in a mathematical structure and propositions about that structure. Set theory, in which a breakthrough in 1963 showed that certain mathematical statements were undeterminable. a direct challenge to the major set theories of the time. This showed that Cantor's continuum hypothesis, cp. 31, is independent of the axioms of set theory, or that there are two mathematical possibilities. One that says the continuum hypothesis is true, one that says it is false. Computability theory, in which mathematicians worked out the abstract theorems that would eventually help lead to computer technology. For example, English mathematician Alan Turing proved an abstract theorem that established the theoretical possibility of a single computing machine programmed to complete any computation. For more information about Turing and computers, see P34 and Math in Computing.
How is wind speed measured?
Wind speed is most often measured using an anemometer. The simplest ones are made with cup-shaped devices that spin and catch the winds. The number of spins translates into an approximate value for the wind speed. The more accurate electronic anemometer has a free-moving turbine suspended in the middle of the instrument that, when held correctly, measures the wind speed. The speed of the turbine sensed by an infrared light relays the signal to an electrical circuit. From there, the wind speed is digitally displayed.
What famous structures were built using mathematics?
Actually, all famous structures needed mathematics. Especially in the initial phases of design and construction. Some of the more famous and exceptionally challenging buildings include the Chrysler Building in New York, a steel frame skyscraper built around 1930 that was the tallest building in the world before the Empire State Building. The Empire State Building in New York, a steel-framed, stone-clad commercial office skyscraper. Built in 1931 that rises 1,252 feet 381 meters high, the Eiffel Tower in Paris, France. Designed by architect Gustave Eiffel and built between 1887 and 1889 as a 985-foot 300-meter-tall exposition iron observation tower. And the Sears Tower in Chicago, built between 1974 to 1976, it is a steel frame with glass stroke. Tower standing at 1,450 feet 442 meters tall and is, to date, the tallest building in the United States. Places such as the Monterey Aquarium, built around 1980 with reinforced concrete and made compatible with surrounding waterfront structures, also needed mathematics in order to be constructed. Of course, when one gets down to it, all types of construction require some math knowledge for them to be built, even a modest piece of cabinetry.
What is the Heisenberg uncertainty principle?
German physicist Werner Karl Heisenberg, 1901 to 1976, not only helped with the quantum theory of light waves. He also developed the Heisenberg uncertainty principle. This states that it is impossible to determine, at the same time, both the energy and velocity of a particle.
How are some parts of an axiomatic system further defined?
There are several terms that further define an axiomatic system. All of them are slightly intertwined, depending on the system. The absence of contradiction or the ability to prove a proposition. Statement, and its negative are both true is known as consistency. Independence is not necessary to an axiomatic system, but consistency is definitely necessary. The opposite of consistency in an axiomatic system is inconsistency. An axiomatic system is called independent if no other axioms can be derived or proved from other axioms in the system. In other words, the entire axiomatic system will be termed independent if all of its underlying axioms are independent. The independence of a system is usually determined after the consistency. An axiomatic system that is dependent has some axioms that are redundant. This is also called redundancy. An axiomatic system is complete if no additional axiom can be added to the system without making the new system dependent or inconsistent. In other words, the aim is to prove or disprove any statement about the objects in the system from the axioms alone. In complete systems, every true proposition about the defined and undefined terms can be proved from the axioms. Systems with the logic based on true or false propositions connected by and or, and not are complete, as are those that include quantifiers. More complex systems, such as set theory, are not considered complete.
What is the definition of a clock?
A clock, from the Latin clicca, or bell, is an instrument we use for measuring time. There are actually two main qualities that define a clock. First, it must have a regular, constant, or repetitive action, or process, that will effectively mark off equal increments of time. For example, in the old days before our battery-driven, analog and digital clocks and watches, clocks included marking candles in even increments, or using a specific amount of sand in an hourglass to measure time. Second, there has to be a way to keep track of the time increments and easily display the results. This eventually led to the development of watches, large clocks such as Big Ben in London, England, and even the clocks that count down the new year. The most accurate clocks today are atomic clocks, which use an atomic frequency standard as the counter.
Who was Carl Friedrich Gauss?
German mathematician, physicist, and astronomer Carl Friedrich Gauss. 1777 to 1855, also seen as Johann Carl or Carl Friedrich Gauss, was considered one of the greatest mathematicians of his time. Some have even compared him to Archimedes and Newton. His greatest mathematical contributions were in the fields of higher arithmetic and number theory. He discovered the law of quadratic reciprocity, determined the method of least squares. Independently of French mathematician Adrien-Marie Legendre 1752–1833. Popularized the symbol I as the square root of -1, although Euler first used the symbol. Did extensive investigations in the theory of space curves and surfaces, made contributions to differential geometry, and much more. In 1801, after the discovery, and subsequent loss, of the first asteroid, Ceres, by Giuseppe Piazzi, he calculated the object's orbit with little data. The asteroid was found again thanks to his calculations. He further calculated the orbits of asteroids found over the next few years.
What does point-slope equation of a line refer to in analytic geometry?
A point-slope equation of a line refers to Cartesian coordinates, if a point has coordinates x1, y1, on a line and a slope equal to m, then the equation y1 equals m, x1, is the point-slope equation. Point-slope is most often used when finding an equation of a line.
What were some early units used for calculating length?
The earliest length measurements reach back into ancient time, and it is a convoluted history. Some of the earliest measurements of length are the cubit, digit, inch, yard, mile, furlong, and pace. One of the earliest recorded length units is the cubit. It was invented by the Egyptians around 3000 BCE and was represented by the length of a man's arm from his elbow to his extended fingertips. Of course, not every person has the same body proportions, so a cubit could be off by a few inches. This was something the more precision-oriented Egyptians fixed by developing a standard royal cubit. This was maintained on a black granite rod accessible to all, enabling the citizenry to make their own measuring rods fit the royal standard. The Egyptian cubit was not the only one. By 1700 BCE the Babylonians had changed the measurement of a cubit, making it slightly longer. In our measurement standards today, the Egyptian cubit would be equal to 524 millimeters, 20.63 inches. And the Babylonian cubit, cubit 2, would be equal to 530 millimeters, 20.87 inches. The metric unit millimeters is used here, as it is an easier way to see the difference between these two cubits. As the name implies, a digit was measured by the width of a person's middle finger and was considered the smallest basic unit of length. The Egyptians divided the digit into other units. For example, 28 digits equaled a cubit, 4 digits equaled a palm, and 5 digits equaled a hand. They further divided 3 palms, or 12 digits, into a small span, 14 digits, or a half cubit, into a large span, and 24 digits into a small cubit. To get smaller measurements than a digit, the Egyptians used fractions. Over time, the measurement of an inch was all over the measurement map. For example, 1 inch was once defined as the distance from the tip to the first joint on a man's finger. The ancient civilization of the Harappan in the Punjab used the Indus inch. Based on ruler markings found at excavation sites, it measured, in modern terms, about 1.32 inches, 3.35 centimeters, see below for more about the Harappan. The inch was defined as 1/36 of King Henry I of England's arm in the 11th century. And by the 14th century, King Edward II of England ruled that 1 inch equaled 3 grains of barley corn placed end to end lengthwise. See box on p46 for more about both kings. Longer measurements were often measured by such units as yards, furlongs, and miles in Europe. At first, the yard was the length of a man's belt, also called a girdle. The yard became more standard for a while, when it was determined to be the distance from King Henry I's nose to the thumb of his outstretched arm. The term mile is derived from the Roman mil passus, or 1,000 double steps, also called paces. The mile was determined by measuring 1,000 double steps, with each double step by a Roman soldier measuring 5 feet. Thus, 1,000 double steps equaled a mile, or 5,000 feet, 1,524 meters. The current measurement of feet in a mile came in 1595, when, during the reign of England's Queen Elizabeth I, it was agreed that 5,280 feet, 1,609 meters, would equal 1 mile. This was mainly chosen because of the popularity of the furlong. 8 furlongs equaled 5,280 feet. Finally, the pace was once attached to the Roman mile, see above. Today, a pace is a general measurement, defined as the length of one average step by an adult human, or about 2.5 to 3 feet, 0.76 to 0.19 meters.
What is the factorial of a number?
A factorial is the product of consecutive natural numbers for all integers greater than or equal to 0. Factorials usually start with 1, the symbol for factorial is an exclamation point. For example, 4 factorial, 4, is 1x 2x 3x 4, or 24. In the numerical system, consecutive factorials are 1, 1, equals 1, 2, 2, equals 1x2, 6, 3, equals 1x2x3, 24, 4, equals 1x2x3x4. 120, 5, equals 1x2x3x4x5, 720, 6, equals 1x2x3x4x5x6, 5040, 7. equals 1 x2 x3 x4 x5 x6 x7. 40,320, 8. Equals 1 x2 x3 x4 x5 x6 x7 x8, 362,880, 9. Equals 1 x2 x3 x4 x5 x6 x7 x8 x9, and so on. There are two additional rules: the number 0 factorial, 0 equals 1. And the factorial values for negative integers are not defined. Factorials are most often used in reference to counting numbers. Statistics, especially in probability calculations, calculus, and physics.
How are numbers classified?
The set of natural numbers are also called integers or counting or whole numbers, which are usually defined as the positive and negative whole numbers, along with 0, 0.
What is a linear differential equation?
A linear differential equation is a first-order differential equation that has no multiplications among the dependent variables and their derivatives, which means the coefficients are functions of independent variables. Other terms associated with such differential equations are nonlinear differential equations, which have multiplications among the dependent variables and their derivatives, and quasi-linear differential equations, in which a nonlinear differential equation has no multiplications among all the dependent variables and their derivatives in the highest derivative term.
What are some types of math used in the legal profession?
Lawyers from civil to criminal need to know mathematics for a number of reasons. For example, when an attorney writes a brief for a case, he or she structures his or her argument like a geometric proof, which is similar to proving theorems by presenting all the relevant facts and laws. Statistics and accounting are valuable, too, because many times large amounts of money are involved in estate suits or other such cases. Knowledge of percentages, interest, and so on are needed. As well, to determine fair settlements for all the parties involved. Lawyers even have to delve into the field of logic, especially symbolic logic that helps them interpret bad arguments and fallacies in the courtroom.
What is a statistical test?
A statistical test is a procedure used to decide if an assertion, often called a hypothesis, about a population's chosen quantitative feature is true or false. These tests usually entail drawing on a random sample, or simple random sample, from the chosen population, then calculating a statistic about the chosen feature. From the result, A statistician can usually determine if the hypothesis is true, false, rare, common, or something in between. Overall, for a statistical test to be valid, it is necessary to choose what statistic to use, what sample size, and what criteria to use for rejection or acceptance of the tested hypothesis.
How does one determine the distance and amount of time a trip will take?
There are several ways to determine the distance and amount of time a trip will take. For example, if the traveler knows that his or her car travels 20 miles for every gallon of gas in the tank, he or she could represent the total number of miles it is possible to drive based on how much gas is put into the tank. This can be expressed as 20G, in which G stands for the number of gallons in the tank. For example, if someone bought 10 gallons of gas to reach a destination, 10 gallons x 20 miles/gallon, the traveler can go about 200 miles. The gallons in the top and bottom of the equation cancel each other out, leaving miles. Another example involves cars and mileage. If the traveler drives down a highway at a steady rate of 65 miles per hour, the driver can determine how long it will take to get to a destination, especially if he or she knows how many miles it is to that destination. The equation is mileage divided by 65 miles per hour, m/65. For example, if the traveler is going 650 miles, the 650 miles / 65 miles per hour equals 10 hours, the miles in the top and bottom of the equation cancel each other out, leaving hours.
What is a tensor?
A tensor is a quantity that depends linearly on many vector variables. They are considered to be a set of n components that are functions of the coordinates at any point in n-dimensional space. Tensors are used in several fields of mathematics, such as the theory of elasticity, stress and strain, and mathematical physics, especially with regard to the theory of relativity.
What is the millionaire calculator?
The millionaire calculator, invented in 1892 by Otto Steiger, saved many of the problems associated with other devices' multiplication. While earlier machines required several turns of their calculating handle to multiply, the millionaire multiplied a number by a single digit with only one turn of its handle. Its mechanism included a series of brass rods varying in length. These rods executed functions based on the same concept as Napier's bones. For more about Napier's bones, see above. The calculator was a hit, and around 4,700 machines were manufactured between 1899 and 1935. the slide rule was not immediately embraced by scientists, mathematicians, or the public. It took until about 1850, when French artillery officer Victor Meyer-Amédée Mannheim 1831 to 1906, standardized the modern version of the slide rule, adding the movable double-sided cursor that gives the slide rule its familiar appearance. Slide rules were used for many decades as the major calculator for the sciences and mathematics, and ranged in shapes from straight rules to rounded.
What is the casino's or house edge?
A casino is a gambling facility that normally includes all or a combination of the following: slot machines, video games, card games, and other games such as Keno, craps, and bingo. In order to make the casino the major money maker, not the gambler, there are certain rules of the casino, including the casino's edge, otherwise known as the house edge. The house edge is the ratio of the expected player loss to the initial amount bet. It is an exact measurement, usually expressed as a percent, of the casino's advantage in a game. A casino earns money by paying winners at house odds, an amount that is slightly less than the true odds of winning the game. There are definitely exceptions to this rule, which is why there are professional gamblers. But the majority of the time, the casino has the advantage. For example, if the house edge for blackjack or slots is 5%, then for every $100 bet initially made, the player can expect to lose $5. This not only helps the casino, but it is sometimes a way for patrons to compare one game to another, and even estimate how much they may lose. Of course, this is not always so straightforward. Some people win and others lose in the short run, but the casino always wins in the long run. There are also exceptions because of the way a game is played, such as in craps, see below. The best scenario would be to have no house edge, or an edge against the house.
What does the greatest common factor mean?
The greatest common factor, or GCF, sometimes called highest common factor, of two whole numbers is the largest whole number that is a factor of both. Take, for example, the numbers 12 and 15, the factors of 12 are 1, 2, 3, 4, 6, and 12, the factors of 15 are 1, 3, 5, and 15. Therefore, the common factors or numbers in both lists of factors are 1 and 3, and the greatest highest common factor in this case is 3. There is another method used to discover the GCF. Listing the numbers' prime factors, then multiplying those numbers. For example, the prime factorizations of 12 and 15 are 2x equals 12 and 3x5 equals 15. Notice that the prime numbers have 3 in common, thus, the GCF is 3. An example with larger numbers is 2. Find the GCF of 36 and 54. Working it out by the first method. The factors of 36 are 1, 2, 3, 4, 6, 9, 12, 18, and 36. The factors of 54 are 1, 2, 3, 6, 9, 18, 27, and 54. The greatest, or highest, common factor of both numbers is to work it out using prime factorization. The prime factorization of 36 is 2x 2x 3x 3, the prime factorization of 54 is 2x 3x 3x 3. Both these factorizations have 1 2 and 2 3's in common. Thus, we multiply those common numbers, or 2x 3x 3 equals 18.